Okay, welcome to tonight's video brought to you by Insomnia. It's actually, I was considering doing a cool problem, and this is one of a purse, which is located at a radius 2 meters from the center of a circle, and a wallet that is at a radius of 3 meters from the center of a circle. These two objects are undergoing uniform circular motion because they rest on the floor of a merry-go-round as the ride goes round. We're told that these two objects are at the same radial point and same radial line. So that means if you were to sit at the center and observe the purse, the wallet would also be on the same line of sight. Okay, and at one instant, we're told that the acceleration, the centripetal acceleration of the purse is given by that in unit vector notation, and then we're asked to find the acceleration of the wallet at that same instant. First things first, we know the acceleration of the purse will have a direction toward the center of the circle. Because these two objects are they rely on the same radial line, we conclude that the direction of the centripetal acceleration for the wallet would also point in the same direction, that is toward the center. So if we could find the direction of the purse, we basically have the direction of the wallet. And over here, I have, in anticipation of this fact, prepared this representation of the vector, the acceleration vector of the purse. And the angle I have represented with alpha, so I can calculate what alpha is, and alpha will be given by, in this case it will be tangent of alpha will be given by the ay component over the ax component, which basically would give us, this is going to be 4 over 2, and then we could conclude that alpha will be the arctan of 2. Whatever this value is, that's not important right now. The fact is we can obtain it. Another thing which, again, in anticipation we need to know is the magnitude of this centripetal acceleration at this instant. That is the centripetal acceleration of the purse. And obviously that's quite easy to find. This would be given by that, which will be 2 to the power 2 plus 4 to the power 2. And this will give us the square root of, this is going to be 20, square root of 20 meters per second squared. So this is the magnitude, and we have the magnitude and the direction right now. So the direction is over there and the magnitude is over there. Now these facts, so far we have details about the purse, but the question asked us to find the acceleration of the wallet. One of the cool things is that because these two remain are resting on the merry-go-round, whichever direction they go in, let's say counterclockwise for simplicity, one of the cool things is that because they stay on the same radial line, that means the period of the purse is going to be the same as the period of the wallet. That is, if the purse takes 2 minutes to go around, the wallet would also take 2 minutes to go around. So, how do we capture that? We capture that mathematically by simply saying the period of the wallet is going to be the period of the purse. But we know that period is defined by 2 pi times the radius at which the wallet is located over the speed of the wallet, and this should also be equal to 2 pi r, this time of the purse, over the speed of the purse. And of course we could clean things up here. Another fact we know is that the speed of the purse or of the wallet is related to the centripetal acceleration via this formula. Oops, let's do that. Let's say, basically we're going to employ this formula for either side of this given equation. And what that would look like, first of all, let's cancel these two out. We will end up with the radius of the radius at which the wallet lies over the speed. This would be nothing more than the centripetal acceleration, the magnitude, that is, of the centripetal acceleration for the wallet times the radius at which the wallet lies. And this would be the square root of all this. And the same thing over here. So basically I've just reused these two formulas for each of these cases. And here we could clean up our formula by squaring both sides, and doing so would mean we will have A W over R W. This is going to be AP of the purse over RP. So what I've done here is I've squared both sides, and I've inverted the formula. So what was the denominator is now the numerator, and what was the numerator is now the denominator. And then we're in the good position now to find the magnitude of the centripetal acceleration of the wallet, and this is going to be given by RW over RP times A sub P. We know the radius of the wallet is 3, and that of the purse is 2. And also we know the acceleration of the centripetal acceleration of the purse, that is given by the square root of 20. So basically we have the magnitude of the centripetal acceleration for the wallet, and if we have the magnitude of that, we can use this angle over here to find its components. So what will the component, the x component of this of the centripetal acceleration of the wallet be? Well, that is going to look like this. So maybe let's partition this for clarity. So the A sub W of x, that is the x component of the centripetal acceleration, is going to be given by the magnitude, which is AW cosine of alpha. And AW of sub y is going to be AW, again this is, that AW is this value. It's this value that we would obtain here, times the sine of alpha. And then we would be in a good position to write this vector in unit vector notation. So we would have A Wx I hat plus A Wy j hat. And here we would have arrived at our destination. I hope that helps you out. It's actually one of the cool problems I thought would be useful to discuss. Anyway, see you in future videos.